So since we started equilibrium, we've talked about quite a few different types of Ks. We've talked about Kc, which is a concentration equilibrium constant. We've talked about Kp, which is our concentration when we have pressure information. We've talked about Keq. We've mentioned that one before. Now we're going to introduce two different types. We've also talked about Kw. Okay. And we've talked about Ksp, the solubility product constant. So that's 5 already. We're going to introduce two more, the Ka, the acid dissociation constant, and we're going to talk about Kb, which is the base dissociation constant, and their relationship to Kw. Okay, so in general, if I have an acid, Ha, any acid, so the anion could be anything. I have something that can deliver an H plus and some counter ion, which is going to go to A minus, the conjugate base. If I put that in water, it's going to dissociate. If it's not a strong acid, it's going to be in equilibrium for that, and I can write the equilibrium expression, which only includes things that actually have concentrations, things that are aqueous, and not include the liquid H2O in it, and I can write a Kc for that reaction as it's written. And we're going to give this K a special letter designation. We're going to call this the acid dissociation constant, and we're going to call that the Ka. So in your book, there's a table of all these different Ks. You need to use this table to get the correct answer on any WebAssign problems or any worksheet problems. And what I want you to realize is two things from this slide. The first one that's written down here is the greater the value of the Ka, the stronger the acid. That means that the equilibrium favors more to the right side, the larger that value is. All right? They're all small numbers, but the larger it is, the more acidic it is. And what I want you to not lose sight of, which way too many students do, is when we talk about a Ka, there's a reaction associated with it. So all these equilibrium reactions, I can write the K for each one of those, and that equals the numerical value that's in the table. Most of you just want the numerical value. You want to crunch your numbers. But I want you to think of it as a particular reaction, and I want you to get good at writing those reactions. It's going to be important. There's going to be questions that are going to be asked based on the equilibrium Ka reaction as well. So a good practice would be to take all of these and write the Ka expression from them for what it actually equals. Okay. So just like a weak acid, if I have a weak base, I have an equilibrium reaction associated with it. So this base in water, now water acts as an acid in this case, I wind up with the conjugate acid of my base. In this case, it's the ammonium ion. And the conjugate base is going to be the hydroxide ion of that. So again, in general, for any base reaction, I could write this Kb expression, or the base dissociation constant. So just to give you an idea of what this would look like, if I have any acid conjugate base, so any A minus aqueous in water, it's going to give me an equilibrium with the Ha plus the OH minus. So remember, if this A minus comes from a weak acid, it wants something from water. So it's actually going to react with the water to protonate that A minus to give me the Ha and generate some hydroxide ion. And I can write the Kb for this reaction, which would be the products over reactants. Remember, we don't include the water, so it's the Ha times the OH minus concentration divided by the A minus concentration. And again, we have tables of these Kb's, and what I want you to not lose sight of is that there's a reaction associated for every single number that's in this Kb table. A lot of times you're going to be given Ka information, but you need the Kb to solve to solve the problem. So you need to know that by writing out the reactions that you have and writing out what reactions you actually need to solve the problem. So again, good practice would be to take all of these and write out that KB expression for each one of them. Okay, so now with all this information, I can relate the Ka and the Kb to each other. And it turns out that if I take that Ka and multiply it by the Kb, it's going to equal the Kw, which we know is 1.0 times 10 to the minus 14th. Okay, so we could actually numerically convert the Ka into the Kb. All right. So let's look at why that's the case. If we look at the expressions that we've written on the next slide, so we have the Ka equals the acid concentration times the conjugate base concentration over HA, and the Kb equals the HA times the OH minus concentration over the A minus concentration. If I just take both of these and multiply them by each other, so the Ka times the Kb is going to equal the H3O plus times the A minus over the HA, and that's going to be times the HA OH minus over the A minus, and that, after I do some crossing out, the A minuses are going to cancel out with each other doing the math, and the HAs are going to cancel out with each other. And what I wind up with is the H3O plus concentration times the OH minus concentration, which equals the Kw.